Hi class. For the last section of chapter 6, we're going to take a look at the 4 ways that we can get air to rise. I think we've talked about all of them, some in more detail. But the first one is one that I know we've talked about a lot in detail, and I'm going to add all of the detail to this figure to show you how far we've come in this particular class. Okay, so a lot of these concepts are going back to chapter 3. And again, this is why I love teaching this class, because everything builds on what we've learned previously, and everything's important. I know I'm biased there, but everything's important. And it just is so cool how this all works together. Okay, so let's talk about the first way to get air to rise is through convection. And so convection all starts with the sun. So solar radiation leaves the sun, and what reaches the top of the Earth's atmosphere is 7% ultraviolet radiation, 43% visible radiation, and 49% infrared radiation. Okay. Now, that solar radiation reaches the top of the Earth's atmosphere, and there are certain fates, 3 fates of solar radiation as it passes through the Earth's atmosphere. Remember that it can be reflected, and that is 24% on a global basis of incoming solar radiation is reflected. It can be scattered, and 7% of incoming solar radiation on a global basis is scattered. It can be absorbed, and 20% of incoming solar radiation on a global basis is absorbed as it passes through the Earth's atmosphere. So of all the radiation that passes through the top of the Earth's atmosphere, 51% never makes it to the Earth's surface. Okay, it either gets reflected away, scattered away, or absorbed by gases in our atmosphere. So 51% of incoming solar radiation on a global basis never makes it down to the Earth's surface. Okay, so that leaves 49%. So 49% on a global basis of incoming solar radiation is absorbed by the surface. Absorbed, spell it right, absorbed by the surface. Okay, and we learned that whenever any object, the Earth's surface, absorbs any form of radiation, whatever ultraviolet, visible, or infrared radiation is left over, this is going to be converted to heat energy. So that 49% of incoming solar radiation that's absorbed by the surface is converted to heat. Okay, and that's going to warm the surface. Okay, by warming the surface, this is going to create a temperature gradient. And whenever a temperature gradient is established, heat will be transferred. Okay? So heat energy is transferred. Okay, and so let's represent heat energy being absorbed by the surface by these red dots, like we've done before. Okay, so heat energy here in this diagram is concentrated near the Earth's surface, creating a temperature gradient, and so we're going to transfer that heat energy into a thin layer of air that's in contact with the ground. It's also transferred into the ground. And again, we're not going to do much with that one. We're not as mesmerized by that heat energy, but certainly it is transferred into the ground too. So let's represent a thin layer of air that's in contact with the ground here. so in contact with the surface, okay? And so when we build up this heat energy right at the Earth's surface, okay, that's going to create the temperature gradient. Heat's going to be transferred, and in this particular case, that heat energy is going to be transferred through conduction. Okay. So slow transfer of heat energy from molecule to molecule from the Earth's surface into a thin layer of air that's in contact with the surface. Okay, and so this conduction will warm the air that's in contact with the Earth's surface. Okay, this is going to make it makes it less dense. Okay, and this is going to lead to convection. Okay, so there's a couple, we can go two routes here, and I'm trying to think what's the best direction to go. So let's start off here at the surface. Okay, so in this thin layer of air, you got to remember that there is evaporation taking place. So transpiration from trees, transpiration from crops, evaporation from the surface, evaporation from an open water surface such as the ocean, lakes, rivers, that sort of thing. So we've got evaporation taking place here. And remember this evaporation, remember the energy component of it is that 600 calories of energy for every gram of water that is evaporated. Okay, this is absorbed. So 600 calories of energy per gram of water that is evaporated are absorbed. Okay, all right. So now we've got water vapor, and I can represent that by these little dots here. This is the water vapor. This is the humidity that is in this thin layer of air that's in contact with the Earth's surface. And that water vapor got into the air through evaporation, which required the absorption of 600 calories of energy per gram. Okay. Now, if you also remember that when we look at the energy balance within the Earth atmosphere system, there is a surplus of heat energy at the Earth's surface. There's a deficit of heat energy in the Earth's atmosphere. So we have to transfer that surplus of heat energy from the surface into the atmosphere. Okay, and one way to do that is through sensible heat. And so remember that here we go with convection. So that's what we're talking about here. This whole figure is all about is convection taking place. One way to get air to rise is through convection. Okay, and so off to the side here, we'll just remind ourselves that this conduction that is taking place from the Earth's surface, conduction of heat energy from the Earth's surface into a thin layer of air that's in contact with the ground, plus which warms up that air, makes it less dense, leading the air to rise through convection. Conduction plus convection equals sensible heat. Okay, so one way that we will transfer the surplus heat energy that we find at the Earth's surface into the atmosphere where there's a deficit of heat energy is through sensible heat. Another way that we transfer that surplus heat energy from the surface into the atmosphere is through latent heat. So we absorb 600 calories of energy for every gram of water that's evaporated. Okay, that hitches a ride in convection. Okay, now let's take into account what we've learned in chapter 6, that when this air rises through convection, we get the air ascending. When the air ascends, the pressure decreases. When the pressure decreases, the air expands. Okay. When the air expands, the density decreases. When the density decreases, the temperature decreases. Okay. At first, that temperature decreases at the dry adiabatic lapse rate as long as the air is unsaturated, okay? Which is 10 degrees C. The air is going to cool at a rate of 10 degrees C for every 1,000 meters that it travels, okay? Now, if we assume that we reach a point in the atmosphere, okay, where we become saturated, we form a cloud. Okay, not a very good looking cloud, but it's a cloud, okay? And this point right here at the cloud base, okay, we call that the LCL, the lifting condensation level, okay? And at the LCL, all kinds of really cool things occur, okay? So first of all, we had to hit saturation, so saturation occurs at the LCL, okay? What does that mean? It means that the relative humidity equals 100%. Okay? If the relative humidity equals 100%, that means that the dew point temperature now equals the temperature. So the dew point temperature and the temperature are equal at this point at the LCL, okay? And if the dew point equals if the dew point temperature equals the temperature, that means that the mixing ratio equals the saturation mixing ratio, okay? That occurs when we reach 100% relative humidity, okay? At this point, when the mixing ratio and the saturation mixing ratio are equal, condensation occurs. Okay, when condensation occurs, this is going to release 600 calories of energy for every gram of water that's released. So remember, we absorbed energy, 600 calories of energy, 600 calories of energy for every gram of water that's evaporated. And when we condense it, we release that 600 calories of energy per gram in condensation, okay? So that's carrying surplus heat energy from the surface into the atmosphere, okay? And when we release that, we are literally releasing heat energy into the atmosphere. And so if this air continues to rise, and it very possibly will, it likely will, it's still going to cool, but we have to now switch. It's going to cool at a slower rate. We're going to switch to the moist adiabatic lapse rate, which is, we're going to say 5 degrees C per 1,000 meters. Okay? All right. Can you believe it? I mean, this is what we've learned going back to Chapter 3, Chapter 4, Chapter 5, parts of Chapter 6. Okay? And we can continue this in Chapter 7 when we talk about clouds and precipitation in Chapter 7. So I love this class because everything fits in so nicely and everything is so logical. It's just incredible to me. Okay? So hopefully you get as excited as I do. I don't blame you if you don't, because I get really geeked up about this stuff. But look at what you've learned so far this semester and see how it all ties together. Okay? So next video, we're going to take a look at the second method in which we can cause air to rise.